Going on to the last problem here in 3-4, continuing on. This is a real world problem. This is called either maximizing or minimizing a function. This is kind of where linear programming is related. It says, as a receptionist for a veterinarian, one of Dolores' tasks is to schedule appointments. She allots 20 minutes for a routine visit, 40 minutes for surgery. The vet cannot do more than 6 surgeries per day. The office has 7 hours available for appointments. If an office visit costs $55 and most surgeries cost $125, find a combination of office visits and surgeries that will maximize. So we're looking at maximizing. So the biggest, the income the vet practice receives per day. So I kind of labeled this out in steps. We're going to define some variables here as our first step. So we're going to I'm going to use V, and that's going to stand for the number of office visits. So the number of office visits. And then we're going to use S for the number of surgeries. So visits and surgeries. That's really the two things we're dealing with. Write a system of inequalities. Now, V and S, we can't have negative office visits, so V and S must be greater than 0. So we know a couple things, that V has to be greater than or equal to 0, and S has to be greater than or equal to 0. And as you can see from my graph, we're only in the first quadrant, we don't have any negative values. Okay, so we know those two are true. Now, what we're going to do is we're going to write an inequality . We're going to write an inequality for this. The office has 7 hours available for appointments. Now, notice that they're in 20 and 40-minute increments. So what we're going to do is we need to think about 7 hours and how many minutes that is. Well, there's 60 minutes in an hour, so if I do 7 times 60, that's 420 minutes we have available, or that the office that she's got available to schedule appointments. We need to be kind of in the same unit here, so it's 420. So what we're going to do is we're going to write a third one here, and we're going to tie in, okay, it's 20 minutes for an office visit, so 20V, and then we're going to add on, so kind of look at a combination of office visits and surgeries, 40 minutes for a surgery, so 40S, and the most we have available is 420 minutes. So that has to be less than or equal to 420. So this will be the number of minutes for office visits, 20-minute appointments times how many, plus 40 for surgeries times how many surgeries. And that total, that combination, when I add them together, has to be less than or equal to 420. And we also know this, one other thing, that the number of surgeries has to be less than or equal to 6. If you remember back up in the problem here, not do more than 6 surgeries per day. That means the number of surgeries has to be less than or equal to 6. Now, if you think about these three right here that we wrote, these three, those are horizontal and vertical line. Notice S is on the horizontal axis, V is on this axis. So basically, V is greater than or equal to 0. That's a vertical line. I'm sorry, that's a horizontal line right here at 0. So we're here. S is greater than or equal to 0, so S is on the horizontal axis, so that would be this line right here. So basically that's the two axes. And then we also know that the number of surgeries has to be less than or equal to 6. So that means a vertical line here at 6. Let me erase that out of there. Okay. So now we got to graph it, or we got to do this other one. So we're going to graph it now. Down here where it's, so I'm starting to do step 3 here is graph it. But this one we need to solve. Okay, now notice on my y-axis is V. So I'm going to solve this for V. So this one right here, I'm going to solve for B. So I'm going to subtract 40S. subtract 40s. So I have 20V is less than or equal to negative 40s plus 420. So now I'm going to divide by 20. I'm getting this in slope-intercept form. Normally we solve for y, but on the y-axis is v, the office visit. So that's why I'm solving for v here. So v is less than or equal to, it'd be negative 2s, negative 40 divided by 20, plus 21. So this is that equation, or not equation, that inequality in slope-intercept form. So 21 would be the y-intercept, so we're right there. We're going to go down 2, right 1 is my slope. So down 2, right 1. So down 2, right 1. 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 Oops, I went down. I'm off on my points there. Let me redo those. I went down 2 and right 2 before. So let's redo that. So I'm going to go down 2, right 1, 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 and so on. So we're like this. Okay, so I'm going to draw that line. So let me grab my line. I'll make it red here. So we're just like that. Notice we're going to shade below that. So basically the region I'm talking about, and let's use green again, is this region right here. This is our feasible, what we call our feasible region. Okay, right in there up to that line. So, because we're greater than the two axes, so that means to the right and above. We're to the left, can't have more than 6 surgeries, and then we're below that line because this one right here means we shade below. It's away from V, and V is our y-axis, so we're shading below. So what we want to do is we want to look at our vertices. Find the coordinates of the vertices. So I want this point, I want this point, I want this point, and I want this point. So we have 0, 0. We have 6, 0, which would be this point right here. We have 6, 9, which is this point. If you notice, this point right here is 6, 9, and then the one on the y-axis is 0, 21, the y-intercept. Now we have to write a function to be maximized or minimized. Now on the ones we did that weren't word problems, they gave that to you, but here's what we're going to do. And normally it's x, y, but we have s as our x-axis, on our x-axis, v on our y-axis. And we got to write a function. If an office visit costs $55, and surgeries cost $125, we're going to do 125 times the number of surgeries plus 55. So the amount of money times each of those, times the number of office visits. So there's our function to be maximized. If you notice, I have a table here, kind of like we did tables on the other one. So we're going to put these 4 in. 0, 0, 6, 0, 6, 9, and 0, 21. So there's our function in the middle. So here I have 125. So you plug in your values, times 0, plus 55 times 0. Obviously, if I don't do any office visits or any surgeries, I'm not going to bring in any income. So this is really the income here. 6, 0 would be 125 times 6 plus 55 times 0. Well, that's going to be 0. 125 times 6 is $750. So if I do 6 surgeries, no office visits, it's $750. If I plug in my next points, 125 times 6 plus 55 times 9. If you do that, 125 times 6 plus 55 times 9, you should get, and you can test it on the calculator, but you get $1,245. And then if you do 0, 21, you do 125 times 0, so no surgeries, plus 55 times 21. So 21 office visits at $55 each. So basically the 125 times 0 cancels out. 55 times 21 is 1155. So the whole problem stated, if you remember right, let me actually scroll back up there. The problem stated maximize the income. So we want to look for the maximum. So I want to look at these four, which were the inputting the values from my vertices, and find the biggest. And right here, if you notice, 1245 would be the maximum income. So $1,245 is the max. Okay, that occurs at the coordinate 6, 9. What does that mean? That means the maximum income is $1,245, so this is where they'd earn the most money, when she schedules. Now, what do those numbers mean? Notice 6 surgeries, and 9 office visits, because of that right there. Okay, so this is just a real-life application dealing with linear programming.